Bismillahirrahmanirrahim. Assalamu alaikum. Here we have example 3 from number theory. This example states that show that every integer is of the form 3n plus 1 or 3n minus 1. In other words, we can say every integer can be written in one of the three form 3n plus 1, 3n minus 1. So we have to verify that every integer can be written in this form. We know about the Euclid's theorem. If the integer a is divided by the positive integer b such that if k is the quotient and r is the remainder, then the Euclid theorem is denoted by a is equal to bq plus r, where this r is the remainder and it will be less than the divisor b greater or equal to 0. So using the Euclid's theorem here, let a and b be two integers with b a positive integer, then by Euclid's theorem, if a is divided by b such that if k is the quotient and r is the remainder, then this r will be less than the divisor b and r will be greater or equal to 0. This k and r both are positive. Since here we have multiple of this 3 is a multiple of 3 and this 3 is also here and it is also here, so putting b is equal to 3 in the Euclid's theorem, we get a is equal to 3k plus r. This k is the quotient and this 3, now this 3 is the divisor and this r will be less than 3 greater or equal to 0. For this b we substituted b is equal to 3, so this r is less than 3 greater or equal to 0. Since value of r starts from 0 and these values are 0, 1, 2, 3, the value of r starts at 3 and these values are 0, 1, 2. Now putting the value 0, 1, 2 in this equation, moreover replace k by n. Here we have integral variable n, so replace this k by n. We get for r is equal to 0 and k is equal to n. This equation becomes a is equal to 3n. Now if r is 1 and k is n, then this equation becomes a is equal to 3n plus 1. Now if r is 2, this here we have r is 2, then by putting here we get a is equal to 3k plus 2. This 2 can be written as 3 minus 1. Now from these two terms taking 3 common, now replace k plus 1 by n, so this a is equal to 3n minus 1 where n is equal to k plus 1. Hence here we have integers. This integer a have been expressed in the form of 3n plus 1 or 3n minus 1. Hence every integer can be written in the form of 3n plus 1 or 3n minus 1 where n is an integer. Here we have a problem. Prove that a minus b divides a power n minus b power n for all n greater or equal to 0, where a, b, n are integers with a not equal to b. Applying the principle of mathematical induction, we have for n is equal to 0 here. So let us use the principle of mathematical induction for n is equal to 0, putting here n equal to 0. So on simplification we get 0, and obviously this a minus b divided 0, which is true because every integer always divides 0 for all a belong to z. Since this is a true result, hence we can say that this statement is true for n is equal to 0. Suppose that the statement is true for n is equal to k. In this step we simply replace n by k, so a minus b divides a power k minus b power k. From this expression we can write this a power k minus b power k equal to a minus b times some integer. This image integer. We now prove that the statement is true for n is equal to k plus 1. So this expression we take this expression here par n is equal to k plus 1. Now simplifying, this can be written as a power k into a, this can be written as a b power k into b. Now here we have, this result is the supposition. So this in this these two terms we have to add and subtract. What this is a power k and here is a, so taking a dot b power k, and here we will use a dot b power k minus b into b power k, क्योंकि यहाँ पे सपोजिशन में a पावर k के साथ b पावर k है माइनस में, तो इसी a पावर k इंटू a के साथ हम a इंटू b पावर k लगाएंगे। यहाँ a हमने इस वजह से लगाया कि ये दोनों a हम कॉमन निकालें और हमारे पास यहाँ पे वो सपोजिशन वाला एक्सप्रेशन यहाँ पे हासिल हो। अब इन दोनों से हम b पावर k कॉमन निकालते तो ये आ गया। अब यहाँ पे सम ऑफ टू टर्म्स है, इन दिस ब्रैकेट इज द सपोजिशन दैट इज a minus b divides a power k minus b power k. So this one is divisible by a minus b. Moreover, this product is divisible by a minus b. Obviously, this a minus b is divisible by a minus b. So also this product is divisible by a minus b. Hence, this expression is divisible by a minus b. It means that this one is divisible by a minus b. Since a minus b divide this expression, it is the assumption, so also a minus b divides this product, because if a divides b, then a divides bc. Also, this a minus b divides a minus b into b power k. We have this term is divisible by a minus b, this term is also divisible by a minus b, and their sum is also divisible by a minus b, implies this one is equal to a power k plus 1 minus b power k plus 1, that is a minus b divided this expression, which means a minus b divides a power n minus b power n power n is equal to k plus 1. Thus the statement is true for n is equal to k plus 1. Also, by principle of mathematical induction, the statement is true for all n greater than or equal to 0, and that statement is a minus b divides a power n minus b power n. This is true for all integers either 0 or greater than 0. Now here we have another question. Prove that a plus b divides a power n plus b power n, where a, b, c are integers. This a not equal to minus b, because if we simplify we get a plus b not equal to 0, and here this a plus b should never be equal to 0, that's why a is not equal to minus b. And here n is positive odd integer, n is a positive odd integer, these are odd integers, and these are positive odd integer. We will prove the problem for n is equal to 1, n is equal to k, and n is equal to k plus 2. By mathematical induction, we have for n is equal to 1, so putting the value here, this will be equal to a power 1 plus b power n is equal to a plus b. So this a plus b divides a plus b. This is true because every integer divides itself. So the given statement is true for n is equal to 1. Suppose the statement is true for n is equal to k. In this step we simply replace n by k, that is a plus b divides a power k plus b power k. Now we prove the statement for n is equal to k plus 2, and now that is we have to prove a plus b divides a power k plus 2 plus b power k plus 2. This is the supposition, and if a plus b divides this one, then there will be some integer such that this expression will be equal to a plus b times m. This is equation 2. Now this is the last step of the mathematical induction. Now simplifying, we can write a square a power k plus b square b power k. Now a power k plus b power k, so taking help from here, and we will add and subtract two terms here. So we get a square a power k plus a square b power k. If this is this term has been here, so we must subtract this term also here, and this last one is this term. Now taking common from these two terms, so we get a square into a power k plus b power k. Taking common here also, we get minus b power k, a square minus b square. Now this a power k plus b power k is this one. This is the supposition, so putting its value, and this can be written as this one. Now taking common, the common is a plus b, and these are the uncommon. Now here we have an equation. This expression is equal to a plus b times this one. This is integer, this is integer. It means this a plus b will divide this left side where this bracket is integer. This is the statement sk plus 2. That is the given statement is 2 power n is equal to k plus 2. That is a plus b divides a power n plus b power n power n equal to k plus 2. Also, by principle of mathematical induction, a plus b divides a power n plus b power n for all odd integers n, for all positive odd integer n.